So now that we've talked about partitioning, how you break a data source up into chunks, we're going to talk about how those chunks are processed in parallel using the common ForkJoin pool. And this will give us the first of several different discussions about how this works. The discussion we're going to do here is primarily focused on how it works with parallel streams. When we talk about ForkJoinPool, which we'll probably start talking about next week, we'll get into a lot more detail about how things work under the hood. But this is intentionally designed to be an easier, higher level discussion that focuses on how streams work and parallel streams work. So the way it works at a high level, when your splitterator breaks up your data source into chunks, those chunks are then passed off to the one and only singleton common ForkJoin pool. And we'll talk later about the structure of the common ForkJoin pool, or any ForkJoin pool for that matter, because they have a very similar structure. A ForkJoin pool is a framework that provides high performance, fine grained, we'll talk more about fine grained in a second, task execution framework for data parallelism. What fine grained really means here is we're going to try to split things up into very small atomic elements, of which there will be lots of, and then those things will be given to the threads, the worker threads in the ForkJoin pool, and then those things will run them to completion. And by having lots of small things, we can keep the CPU maximized. So that's what it means to be fine-grained. And the ForkJoin pool provides the parallel computing engine for lots of stuff. It provides the parallel computing engine for parallel streams. It's one of the options you get by default if you use completable futures. And there are various other Java-oriented frameworks for other languages that use the ForkJoin pool as well. The ForkJoin pool itself implements the ExecutorService interface. We won't talk a whole lot about ExecutorService in this class. It's part of a very powerful framework for thread pool-based computation. Next semester's class will go through this in a lot more gory detail, but for right now, just take it for faith that the ExecutorService is an important framework. And the ForkJoin pool executes so-called ForkJoin tasks. And a ForkJoin task is essentially an object that associates a chunk of data along with a computation on that data to enable fine-grained parallelism. We often think about ForkJoin tasks as something like a SIMD model, single instruction, multiple data. And the best example of SIMD models in my mind is the bank of washing machines or bank of dryers, where you take your clothes and you put them in the washing machines and you have a single instruction, wash your clothes, that works on all your data, your clothes, in parallel, right? So that's kind of, when you think about SIMD, think about washing machines or dryers. A ForkJoin task is similar to, but lighter weight than a Java thread. And I have to say I had a lot of fun coming up with the images for this particular slide. So you can see the ForkJoin task is like the scrawny little brother, and the thread is like the muscular, beefed up on steroids computational element. In particular, ForkJoin task omits a bunch of things you would expect to see in a thread. So it doesn't have a runtime, its own runtime stack. It doesn't have its own registers. It doesn't have its own thread-specific data. It's basically a data structure that's multiplexed over one or more threads in the worker thread pool. So as a consequence, you can have hundreds or thousands or hundreds of thousands of ForkJoin tasks that are going to be executed on top of a small number of Java worker threads in the ForkJoin pool. So that's kind of the way to visualize that. And that's, again, by design. The intent was to do that. If you want to learn more about why it was done that way, you should listen to this interview by my friend Doug Lee, who is an expert who wrote the ForkJoin pool, and he explains the rationale for it. So you can basically think of a parallel stream as a user-friendly facade for the more complex ForkJoin pool framework. So it's kind of a wrapper that wraps it up and makes it functional and easy to program while leveraging all the powerful capabilities that lurk under the hood. It's possible to program the ForkJoin pool API directly, although it can be somewhat painful. Anybody here seen this scene from Lord of the Rings? Come on, you guys, you got to watch Lord of the Rings. So there's a scene where Saruman says to Gandalf, "I have given you the chance to come with me willingly, but you have elected the way of pain." So here, we've given you the way of programming with Java streams, but if you want to elect to program ForkJoinPool, you are now going to have the way of pain. There's some examples, if you really want to see the difference in programming, to compare and contrast ForkJoinPool versus parallel streams, there's an example that uses the ForkJoinPool to implement the search stream gang example app. And I encourage you to look at it because it's pretty crazy. The main reason why you would ever, yes, Abhi.
Earlier you mentioned the frameworks of parallel streams.
Yes.
So parallel streams themselves always use the ForkJoinPool, and then completable features don't necessarily always use it.
Great question. So the question was, what's the relationship between parallel streams, ForkJoinPool, and completable futures and ForkJoinPool? Parallel streams always use the default ForkJoinPool, the common ForkJoinPool. With parallel streams, as we'll see in about 3 weeks, you can use it by default. If you make a completable future, by default it uses the common ForkJoinPool. But if you want to, you can give it your own thread pool instead of having to rely on the common ForkJoinPool. It's a little bit mysterious why they give you the flexibility for one and not the other, but we can talk about that when we get to computable futures. The main reason to use the ForkJoinPool is if you're trying to write a program that doesn't really match well with the parallel streams divide and conquer model. So parallel streams works really well for divide and conquer style things where you split everything in half. But not everything works that way. And so if you take a look at this article, you'll see a different form of parallel computing, which in this case uses the ForkJoinPool, and it doesn't split things in half. And so we'll talk about that in a lot more detail when we get to the ForkJoin part of the class, and you'll get a chance to program ForkJoinPools directly for assignment number 3, which will be up after assignment number 2C is done. All the parallel streams in a process share the common ForkJoinPool. It's important to know why that's the case. There's only one of these things. It allows us to be able to optimize resource utilization by knowing what cores are being used globally within a process. So it's like, Professor X with Cerebro. It can see all the cores and know what they're doing, or Santa Claus. This, they know if the cores have been bad or good each year. I saw this funny thing the other day. It said, if you have kids, it said, put lots of empty boxes and wrap them up with wrapping paper and ribbons. And every time your kids do something bad, throw them into the fire. Not the kids, obviously, the boxes, right? So it's kind of like it's Elf on the Shelf, on steroids for people who want their kids to behave because of fear of Santa. This trade-off between global and local resource management is common in many other things. A good example would be Java garbage collection, which has a global heap that is used to manage the resources. There's surprisingly few, if any, knobs to control the ForkJoinPool, and that's, again, by design. The simplicity is intentional. They wanted to have something very simple that could optimize itself, in contrast to other thread pools like the thread pool executor, which we'll talk about next semester, which is more like Swiss Army knife with lots and lots and lots of different blades and utensils and so on. The ForkJoinPool is more like a spork, right? It's a very simple thing you can use to eat yogurt or steak, with the same utensil. So think about the simplicity, and that's done by design. We will talk shortly, not now, but next week, about how you can configure the number of worker threads in the ForkJoinPool, the common ForkJoinPool. And we'll talk about how to do it either programmatically by setting the number of threads, which works, but it's a bit kind of draconian in some ways. It's kind of a very obtrusive solution because it sets it for everything in the process. And then you can also use something called the ForkJoinPool managed blocker to get finer level control over blocking behavior. Okay, so that's the end of that discussion. We're now teed up to do the quiz.